Imagine having a team of like the world's absolute smartest people. We are talking math geniuses, coding prodigies, top tier analysts, and they are all just sitting in a room waiting for your instructions.
I,
Sounds incredible,
I
right?
absolutely. It sounds like a dream scenario.
Right. But here is the catch. They completely refuse to talk to each other.
Ah, yeah, that is a problem.
Yeah, it really is. And you, sitting at the front of this room, have to figure out exactly who should do what and in what order just to solve a massive complex problem. Like, if you hand a theoretical physics equation to the creative
Do it, you
writer,
fail.
exactly, you fail. If you ask the coder to verify complex historical facts, you fail.
It is basically the ultimate delegation nightmare because, I mean, you have all this raw brain power in the world,
Mm.
right? But without the right manager to direct the workflow, that intelligence is just, it's entirely useless.
And this is the exact delegation nightmare happening at the bleeding edge of artificial intelligence right now. Today, we are doing a deep dive into a really groundbreaking research paper. It's from scientists at Sakana AI, the University of Michigan, and the Institute of Science, Tokyo.
Yeah, it's titled Trinity, an evolved LLM coordinator. And it is a fascinating read.
It really is. So, the mission for today is to explore how these researchers built a tiny, incredibly lightweight AI manager. And this manager basically orchestrates a pool of massive, diverse, large language models, or LLMs.
Right, and they managed to achieve record-breaking performance. And the kicker is, they did it without needing to physically merge the complex, often totally incompatible internal codes of those massive models together.
Which is huge. So to start off, let's talk about the current landscape. Why is merging models even a thing we were trying to do?
Well, the current dominant philosophy in AI has really been guided by what we call scaling laws. Like if you want a smarter model, you train it on more data. You pump in more compute power. You increase the parameter count.
Basically, you just build a bigger, heavier, more expensive monolith.
Exactly. But that approach is becoming brutally resource intensive.
Yeah.
I mean, we are starting to hit practical limits in terms of energy and pure financial cost. So the industry attempted an alternative, a sort of micro-level solution called model merging.
Which is essentially like trying to perform an AI brain transplant, right?
Yeah, that is actually a great way to put it.
Like you are taking the weights, the actual numerical representations of the neural connections from different models, and mathematically fusing them together. If Model A is good at math and Model B is good at coding, you try to just average their weights to get a model that does both.
Right. That is the theory. Anyway, but in practice, this whole weight merging thing is hitting a massive wall for two very stubborn reasons.
Oh, really? What kind of wall?
Well, the first is the API wall. You literally cannot access the internal wings of top-tier closed-source models. The neural architecture for things like OpenAI's GPT-5, Google's Gemini 2.5 Pro, or Anthropic's Claude 4 Sonnet, they are locked completely inside corporate black boxes.
Right, of course. You can send them a prompt and get an answer, but you definitely cannot download their brains.
Exactly. And the second reason is, even if you are strictly using open source models where you do have the weights, their fundamental architectures are often completely mismatched.
Oh, because you can't seamlessly stitch together a model built with, like, a 4096 dimension layer geometry and another built with 520 dimension layers.
Exactly. The math just physically breaks. The matrices simply do not align.
Okay, let's unpack this. So instead of trying to blend an apple and an orange into this weird, structurally incompatible smoothie, Trinity acts more like a head chef.
A head chef. I like that.
Yeah, like it is tasting the recipe at each step and deciding when to hand the mixing bowl to the pastry chef versus the saucier.
Yes. Trinity completely abandons that micro-level fusion of weights. It takes a macro-level approach instead. It basically sits on top of this pool of diverse models and just passes the task around based on who is best suited for the current step of the problem.
Got it. So it treats them like independent tools.
Right. It treats the underlying models as powerful, independent, specialized tools. It coordinates their complementary strengths in the data flow space rather than the parameter space.
And for you listening, think about why that distinction is so crucial. It means you can leverage the billions of dollars already invested in these state-of-the-art models from entirely different corporate providers.
Exactly. And you do not have to retrain or merge a single one of them. You just need a better manager.
Right. But logically, I mean, that manager itself has to be incredibly smart to know how to direct traffic between, say, GPT-5 and Gemini. When I think of a system that can boss around trillion parameter models, I assume it has to be a resource-heavy supercomputer itself.
You would think so, right?
Yeah.
But looking at the paper, Trinity is remarkably tiny.
Tiny, like how tiny?
It is microscopic compared to the giants it manages. The coordinator is built on a small language model, or SLM. Specifically, they used an open source model called Qwen 30.6b.
Okay, wait, so that is 0.6 billion parameters.
Yeah, exactly. And on top of that already small foundation,
Yeah.
they attached what is called a lightweight head that makes the actual routing decisions. That head only has about 10,000 parameters.
Wait, I have to push back here. If this coordinator is so small and the paper notes the coordinator itself doesn't even generate the text, it just reads the prompt and passes it along, how does a 10,000 parameter head know enough about a complex, multi-layered user query to assign it to the right giant model?
That is the big question. And it brings us to the core technical breakthrough of the architecture. It all comes down to leveraging something called hidden states.
Hidden state.
Yes, specifically the hidden state of the penultimate token.
Okay, the second to last token. If you're listening to this and wondering, wait, what actually is a hidden state? Think of it like the moment right before you speak. You've heard a question, your brain has processed the words, contextualized them, and formed a complete, complex idea of the answer.
Right.
All of that understanding exists in your mind as a concentrated thought, but your vocal cords haven't made a sound yet.
That is an excellent way to conceptualize it. As a language model processes your prompt word by word, it is building a deep mathematical representation of context, layer by layer.
Oh, I see.
Yeah, by the time it reaches the very end of your prompt, right before it outputs its first generated word, that internal hidden state is a raw numerical vector, and it contains an incredibly rich semantic summary of everything you just asked.
So the researchers just grabbed that summary.
Exactly. They hypothesized they could simply extract that specific hidden state vector from the 0.6 billion parameter model and feed it directly into their tiny 10,000 parameter head.
Wow. So the small model has already done all the hard work of reading the room. The lightweight head just uses that summary to act as a switchboard.
You got it. And the visual proof they provided for this in the source material is genuinely mind-blowing.
Yeah, they use techniques like TSNE, right? Which basically takes a massive, incomprehensible, multidimensional math problem and flattens it into a 2D map so human eyes can actually see the groupings.
Exactly. And when they mapped out these hidden states using TSNE, the tasks naturally and cleanly separated into distinct mathematical clusters.
Here.
Math problems form one tight visual cluster, coding queries form another, general reasoning forms another.
That is wild.
What's fascinating here is how clean that separation actually is. They ran a linear SVM, which is a really straightforward classification algorithm, on those hidden states. And it scored a perfect 1.00 accuracy for task type classification.
Wait, a perfect score.
Literally perfect. It perfectly separated the types of problems based on nothing but that single hidden state vector.
Yeah.
Because the hidden state is already so perfectly organized, the lightweight head does not need millions of parameters to understand the prompt.
Unbelievable. And to make that coordinator even sharper, the researchers used a technique called singular value fine-tuning.
Yes, exactly.
Instead of retraining the whole neural network to get better at routing, they basically just tweaked the volume knobs, the singular value scales of the existing connections in a few specific layers.
Right, and that kept the total number of trainable parameters under 20,000, which is orders of magnitude smaller and cheaper than typical fine-tuning.
So, okay, we have established how this highly efficient 20K parameter manager perfectly understands the context of a problem using hidden states.
Yeah. But understanding the problem is really only step one.
Right. Knowing the context of a math problem is only half the battle. Because if this tiny manager just points a finger at a giant model and says, solve this, the giant model can still hallucinate, lose track of the math, or skip a step.
Oh, absolutely. They do it all the time.
So how does Trinity actually force these giants to do the work correctly?
By enforcing a highly structured multi-turn protocol, Trinity does not just hand over the prompt and hope for the best. It operates on a tri-role system: thinker, worker, and verifier.
Okay, thinker, worker, verifier.
Yeah. At each turn of the conversation, the coordinator selects a model from the pool and forces it to adopt one of these three distinct personas.
Here's where it gets really interesting. The paper gives a concrete example of a complex accounting problem to show this in action. Let's walk through it so we can see the mechanism.
Sure, let's do it.
Imagine you, the listener, ask this question. Binaco purchased a vehicle on January 1st for $15,000. They estimate they will use it for 8 years with a $3,000 salvage value. Using the double declining balance depreciation method, compute the vehicle's second-year depreciation expense.
Now, for a monolithic model operating on its own, that prompt is a massive trap.
Really? Why?
Because it will often rush straight into calculating the numbers, it'll mess up the compounding formulas or completely forget the rule regarding the salvage value limit. Trinity intercepts that failure by pacing the workflow.
Ah, I see. So turn one, the coordinator reads the query's hidden state and recognizes it as a complex math task requiring a strategy. It picks an LLM from the pool and assigns it the role of thinker.
Exactly. And the thinker is explicitly told not to solve the math. Its only job is to write out a high-level logical plan.
So it outputs something like, Step 1, determine the straight line depreciation rate. Step 2, bubble that rate for the declining balance percentage, and so on.
Step 3, apply the rate to the $15,000 book value for year 1. Step 4, subtract year 1's depreciation from the book value and apply the rate again for year 2.
Okay, so then turn 2 begins.
Yes. The coordinator then takes that thinker's strategic plan, appends it to the evolving transcript, and initiates turn 2. This time, it selects a model, perhaps a different one, that excels at raw arithmetic rather than planning, and assigns it the role of worker.
Got it. So the worker just looks at the thinker's plan and executes it.
Exactly. It simply crunches the numbers step by step, arriving at an answer of $2,812.50.
But we still aren't done.
No, we are not.
Because then we have turn 3. The coordinator takes the worker's final math and calls up another model to act as the verifier. And the verifier's only job is to evaluate if the worker's logic and arithmetic are actually sound.
Precisely. In the paper's example, the verifier reviews the math, confirms the calculations are correct, but also explicitly checks an edge case.
Oh, like making sure it didn't mess up the salvage value.
Yes, verifying that the depreciation hasn't violated the salvage value threshold.
Yeah.
And it notes the standard rule to switch to straight-line depreciation in later years if it yields a higher amount. Only after the verifier formally accepts the result does the system stop and hand you the final answer.
That is so smart. And this separation of roles is vital to the system's performance, right?
Oh, incredibly vital. To prove this, the researchers ran ablation studies. Ablation is basically where you systematically remove parts of an AI system to see what breaks. It isolates the value of each component.
Makes sense. So what happened when they broke it?
Well, when they removed the thinker, role-forcing the system to jump straight to the worker without a pre-written plan, performance on the rigorous Math H500 benchmark dropped by a massive 6 points.
Wow, 6 points is huge.
It really is. Without the thinker, the middle-level strategizing disappears, and this structural integrity of the workflow just completely collapses.
It fundamentally proves that slowing down to plan actually speeds up accuracy.
Absolutely.
But looking at this incredibly sophisticated 5-turn tri-roll protocol, a logical gap immediately jumps out at me.
What's that?
We have a tiny 10K parameter head orchestrating massive models through multiple turns. How on earth do you train that tiny head to make those complex routing decisions without going completely bankrupt?
Yeah, that is a huge hurdle.
Because if teaching by example is too expensive, standard reinforcement learning seems like the obvious choice, right? Just let it learn by trial and error, give it a reward when it gets the final answer right.
You would think so.
Yeah.
But the paper shows that reinforcement learning, specifically algorithms like reinforce, fails spectacularly here. It's due to what is known as the credit assignment problem.
The credit assignment problem,
Yeah.
which is like trying to figure out why a football team lost a game.
Yes, exactly.
Like, if the final score is 0, was it because the quarterback threw a bad pass, the coach called a terrible play, or the kicker missed the field goal? The final score doesn't tell you who actually messed up.
Exactly that. In a 5-turn multi-agent collaboration, if the final answer is wrong, the RL algorithm receives a negative reward. But did the thinker make a bad plan on turn 1? Did the coordinator pick the wrong model for the worker on turn 2? Or did the verifier hallucinate on turn 3?
Right, has no idea.
The learning signals, the gradients, become incredibly noisy because the algorithm cannot effectively assign blame or credit across those discrete multi-turn jumps. The learning curves in the paper for RL are just jagged, high-variance messes.
So it just panics.
Pretty much. The model becomes so confused by the noisy feedback that it essentially gives up and just starts picking agents completely uniformly at random.
Wow. And supervised fine-tuning, where you just show the model the perfect path to take every single time, that is completely off the table because of the sheer math. Because to map out the perfect permutations for a 5-turn collaboration with 7 different models and 3 roles, the researchers calculated it would take around 87 billion LLM queries to generate the labels.
Yeah, 87 billion. You would need the GDP of a small country just to pay the API fees to generate the training data.
Exactly. So if SFT is too expensive and RL is too noisy, what is actually left?
They turn to evolution.
Evolution.
Yeah, specifically a derivative-free black box optimization method called sep-CMA-ES. That stands for Covariance Matrix Adaptation Evolution Strategy.
Okay, we definitely need an analogy for this because
Yeah.
that sounds terrifying.
It is a mouthful.
Think about natural selection in a really harsh environment. Instead of trying to mathematically calculate the single perfect path up a treacherous mountain step by step, which is what RL tries and fails to do, sep-CMA-ES just takes a bunch of mutant hikers and drops them all on the mountain.
I love the mutant hiker analogy.
Right. It watches to see who climbs the highest before failing. It doesn't care why a hiker succeeded. It just takes the physical traits of the most successful hikers, recombines them, and breeds a new batch of hikers for the next generation.
Translating your mutant hiker analogy back to the neural network,
Hmm.
the algorithm takes the volume knobs,
Hmm.
those 20,000 weights in the coordinator's head, and randomly tweaks them to create a population of slightly different managers.
Okay, so lots of mutant managers.
Exactly. It lets all these different managers run the full 5-turn process on a batch of problems. Whichever managers happen to get the highest final score, regardless of how they got there, have their specific knob settings saved and mathematically recombined to create the next generation of managers.
Wow, so it entirely bypasses the credit assignment problem because it doesn't need to backpropagate gradients through the individual turns.
You nailed it. But the paper notes that evolutionary strategies usually struggle with high-dimensional problems.
Yeah, they do.
The reason this specific variant, sep-CMA-ES, works so efficiently here relies on a mathematical property they call block diagonal separability.
Okay, which sounds incredibly intimidating.
It sounds dense, but the core concept is quite elegant. Block diagonal separability simply means that the decisions the manager is making are fundamentally independent of each other.
Independent? How so?
Well, the logic for deciding which agent to pick from the pool does not heavily interfere with the logic for deciding which role to assign to them.
I see. If we connect this to the bigger picture, it is like running a restaurant where the decision of who to hire as the pastry chef doesn't interfere with the decision of what brand of oven to buy.
Exactly. Because those decisions do not cross-contaminate, the evolutionary algorithm can optimize them at the exact same time, in parallel. It doesn't have to calculate every possible complex interaction between the chef and the oven.
Oh, that makes so much sense.
Yeah. By isolating those variables along the diagonal of the matrix, the algorithm avoids exploring dead-end combinations. It makes the evolutionary process incredibly fast and highly computationally efficient.
Yeah.
And that allows the researchers to train this highly capable coordinator on a remarkably tight budget.
So we have the constraint of the API wall, the tiny hidden state architecture, the tri-role execution loop, and the evolutionary training process that makes it financially viable. The ultimate question is, does this elaborate system actually work?
That is the million-dollar question.
Right. Let's look at the benchmarks. The pool of models Trinity was managing is basically the Avengers of AI right now. We are talking proprietary giants like GPT-5, Gemini 2.5 Pro, Claude 4 Sonnet, alongside top-tier open-source models like DeepSeek and Qwen 3.
And the results shatter the current paradigm.
Yeah.
The researchers tested Trinity across a rigorous gauntlet of complex benchmarks spanning mathematics, coding, and graduate-level reasoning. The absolute standout proof of concept occurred on a benchmark called Live Code Bench.
Specifically, the newly released V6 version of Live Code Bench.
Right.
And the reason V6 is so important is that it is a dynamic test containing coding problems published in early 2025. It is essentially a blind test. The constituent models could not have possibly memorized the answers in their training data because the problems did not exist when they were trained.
Exactly. It's totally fresh data. And on that blind test, Trinity hit a state-of-the-art pass at one score of 86.2%.
So what does this all mean? A pass at one score means that on its very first try, with no second chances and no human intervention, the system output the mathematically perfect, fully executable code 86.2% of the time.
Yeah, which is insane.
Just for context on how dominant that is, the best individual monolithic model in the pool on that exact same test was GPT-5, which scored 83.8%. Claude 4 Sonnet only scored 46.5%. Trinity completely blew past the monolithic giants, not by being bigger, but by coordinating them.
Crucially, Trinity demonstrated demonstrated what researchers call emergent generalization.
Emergent generalization, meaning it can handle new stuff.
Yes. It did not just beat the constituent models on the specific types of tasks it was explicitly trained on. They subjected Trinity to zero-shot evaluations, meaning they threw completely unseen, entirely novel types of benchmarks at it without giving it any prior examples to learn from.
Oh, wow. What kind of benchmarks?
They ran it through AIM, which consists of elite Olympiad-level math competitions. They ran it through GPQAD, which tests graduate-level physics, biology, and chemistry.
And how did it do?
On every single one of those unseen zero-shot tasks, Trinity outperformed every individual model in its pool.
It is genuinely more than the sum of its parts.
Its performance actually approaches a fascinating theoretical metric called the per-question best upper bound.
Oh, I read about this. Imagine if you had a magical oracle sitting in the room. For every single question, the oracle instantly knows exactly which of the 7 models is statistically most likely to get it right and just writes the question to that specific model.
Right. And Trinity's performance is incredibly close to that theoretical ceiling of perfect hindsight. Through the evolutionary training of those 20,000 parameters, it has genuinely learned how to deploy the right tool for the right job at the exact right moment in the workflow.
Think about what that implies for you listening to this right now. The prevailing narrative in the tech industry has relentlessly insisted that progress requires finding the one AI to rule them all, the single smartest, biggest trillion-parameter monolithic brain.
Yeah, the one big monolith.
But this paper proves that the future of being highly productive, of being truly well-informed and capable in your own work, is not about relying on one giant brain. It is about effectively coordinating a diverse set of highly specialized tools. It is about the architecture of the workflow, not just raw compute horsepower.
We're witnessing a fundamental paradigm shift here. The frontier of artificial intelligence is moving from merely scaling single models to engineering collaborative AI ecosystems.
It really is. To recap the scope of this deep dive, we started with the physical and financial limits of micro-level weight merging, the impenetrable API walls, and the geometric architecture clashes.
Right.
That constraint forced the creation of Trinity, a microscopic 0.6 billion parameter coordinator that reads deep semantic context by extracting hidden states.
We saw how it manages execution by forcing models into a thinker, worker, and verifier loop.
Yep. And how researchers mathematically bypass the credit assignment problem by training it with evolutionary algorithms,
Yeah.
all of which culminated in record-breaking zero-shot generalization.
It is an incredibly elegant macro-level solution to a brutally expensive micro-level problem.
It really is.
However, this raises an important question, and it is a reality the researchers themselves explicitly point toward in their conclusion. Right now, Trinity is coordinating these massive LLMs to solve math equations and coding puzzles in a highly contained theoretical environment. But the immediate future work they outline involves integrating code interpreters and live APIs.
Wait, meaning the system won't just be generating text, it will be actively executing software.
Precisely. If a tiny 20,000 parameter manager can already orchestrate the world's smartest AI models to systematically break down and solve elite theoretical problems, what happens when these verifiers aren't just checking depreciation math on a digital page, but are verifying and approving actions in the real world?
Oh, wow.
What happens when this autonomous tri-role system is given a financial budget, a live web browser, and permission to act on the conclusions the thinker and worker arrive at? We have built a remarkably efficient manager to sit at the front of a room of isolated geniuses. But how do we, as humans, oversee the manager when that manager is coordinating an entire autonomous ecosystem capable of impacting the physical world?
That is a brilliant and honestly slightly terrifying thought to leave on. You are sitting at the front of that room of geniuses right now, but pretty soon they won't just be waiting for your instructions. The manager will be generating the instructions and the workers will be executing them out in the wild.
It's a brave new world.
It sure is. Thank you so much for joining us on this deep dive. Keep exploring, keep questioning the systems being built around you, and we will see you next time.